Okay, welcome back everyone. Unfortunately, we have to change room again just for one lecture because this room was reserved long ago for this one particular day tomorrow. So tomorrow we will have to be in this other room where we already had the very first lecture. This is somewhat inconvenient room with a whiteboard, but I think for one lecture it will work. Okay, so that's only this lecture tomorrow. Otherwise we are for the lectures here in this room. Okay, let's continue where we stopped last time. We were talking about particles, motion of particles, and at the moment we are talking about massive particles, so not about particles that move with the speed of light, but rather particles which move with a speed smaller than the speed of light. So they have a world line like that. So if I plot here, as we always do it, an inertial system, then the tangent to the world line should always be inside the light cone. So it should be like that. And the length of this tangent is a matter which is determined by the parameter, how fast the parameter proceeds. And we have made a special choice for this parameter, which is called proper time. And if we take the derivative with respect to proper time, then we denote this tangent vector by u mu of tau. So that's what we then call the forward velocity. So let me remind you what this was. So this was u mu of tau, just the derivative of the world line, if parameterized by proper time. And the proper time parameterization was fixed by the condition that eta mu nu u mu should be minus c squared. Must be negative because the u mu is inside the light cone, and we fix the length of this vector by requiring this to be minus c squared. Here obviously this is a velocity, so here I have the square of a velocity, and the natural choice as a unit for the velocity is the velocity of light. And then we have the forward acceleration. Which is usually denoted a mu, which is a derivative of u mu with respect to tau. So that's the second derivative with respect to tau of x mu, second derivative. And on the second worksheet, we made a little exercise with such a world line. The world line we were considering was a particle moving in a circle with uniform velocity. And I hope yesterday you managed to do this. Dennis told me that he had to do sort of a one-man show because nobody else was willing to come to the board. But as he told me, everything worked out fine. So you ran through the full set of solutions. I hope you now have a little bit, some sort of feeling for these notions, for velocity and for acceleration, after having it calculated for one example. And we will do another example together in a minute. But before doing this, I want to prove a general property of the, I would like to also to show the vector mu in this picture. And for that I need some information. I have to know how it is related to the u mu. And the important property which I want to prove is that the a mu is perpendicular to the u mu with respect to the Minkowski metric eta. That's an important property which I now want to prove. And I do this just by differentiating this equation. So by differentiating the equation that minus c squared is eta mu nu u nu, we find what? Well, we differentiate with respect to tau. Differentiating with respect to tau. Maybe I should write the arguments everywhere where they occur. So this is a constant. That has nothing to do with tau. It's just plus or minus ones or zeros. The u mu depends on tau, and u nu depends on tau. So here is a parameter tau, and then I can differentiate with respect to tau. With respect to tau, we find the following. On the left-hand side, obviously, we get a 0. And we do it quite slowly. So I Remember, there's a summation tacitly involved, right? Summation over mu, summation over nu. So what I do is I differentiate the sum term by term. But of course I can do this because of linearity. Yeah. So the summation sign doesn't show up explicitly in any way when I calculate the derivative. I just take the derivative for each summand, and then again I carry through this sum over the indices, which is tacitly understood. And then of course I get this term. And then I get a second term where I differentiate the other one, the nu of d tau. And I want to combine these two things in one term. And of course I can do this just by renaming the indices. Yeah, you remember this mu is summed away. So it is just a summation index on which the whole thing doesn't depend. So I can give any name to the summation index. So in particular, I can interchange the name for mu and nu. Yeah, I can call this summation index mu and the other one nu. And then I see that this is precisely the same as u nu of tau. Yeah, I just interchange the names of the indices. It's exactly the same thing. If you write it out as a sum, if you remember that there's always a sum understood, you see that this is exactly the same thing, right? You have just given other names to the summation indices. So we can combine the two things. It's just two times the same. du mu of tau, u nu of tau. So we have found that this expression, yeah, as one says, the scalar product formed with this eta between this is a mu. Yeah, a mu. That's the scalar product between the 4 acceleration and the 4 velocity is 0. And that's usually expressed in the way that we say a mu is orthogonal or perpendicular to u mu with respect to the Minkowski metric. Yeah? If this would be a delta, a Kronecker delta, oh, I forgot the eta. If this would be a Kronecker delta, then this would just be the usual scalar product in Cartesian coordinates, right? And now it's not the usual Kronecker delta, so it's not the usual Euclidean product, it's some other sort of product which has minus signs in funny places. So that's why we call it the orthogonality with respect to eta, not the standard orthogonality. It's a modified orthogonality. And you have seen in the second worksheet that the geometrical properties are quite different. You have calculated what it means to be orthogonal, or you have drawn a picture what it means to be orthogonal to a vector u mu, which is inside the light cone. And if I remember correctly, you have found that this is something like that. The vectors which are orthogonal form a hyperplane, a three-dimensional hyperplane, which makes the same angle with respect to the light cone as this vector. Yeah? That's what you have found in the, I think it was the first problem in the second worksheet. So the fact that a mu is perpendicular to u mu means that it lies in this hyperplane. Yeah? So in the picture, if you go to another inertial system where u mu makes a different angle with the light cone, then the a mu would move in the corresponding way in the opposite direction. So if u mu goes closer to the light cone, a mu also comes closer to the light cone. So in particular, you see now from the picture that the a mu is always space-like. Yeah? It's always outside of the light cone. The u mu is time-like, it lies inside the light cone, the a mu is outside, it's space-like. So it's a spatial vector in any inertial system. This can also be seen in the momentary rest system. So that's a system where at one particular moment, I have to do this for every moment separately, the u mu is vertical. Yeah, that's what we call the momentary rest system. Then, of course, the a mu is this here, a mu u mu. So this means the a mu has no zero component, right? It has only spatial components. So in the momentary rest system, we have 0. That was the general expression, a mu u nu. And now I can write this as, because this has no zero component, we can, nonsense. I was jumping ahead already. No, slowly. So I go into the momentary rest system. I talked about A. This was jumping ahead. I wanted to talk about U first. So let's look at the U. What is the U doing in the rest system? The U in the rest system has only a zero component. It has no spatial components. Yeah? So the U has only a zero component. So I get eta 0, 0, U naught, A naught, and then I get zeros, because all the other components of U are zero. And this is, of course, just minus U naught, A naught. And U naught, of course, is not zero, because then I would have the zero vector. Yeah, but this is not the zero vector. It must have this non-zero A naught component. So this is not zero, so what we conclude is that the A naught is zero. So that was the conclusion I had already jumped to a step too early. So what we see in the picture also follows from this calculation. The A has no zero component, no temporal component. And from this in particular, we read that it is a space-like vector. So in particular A mu is space-like, which means that eta mu nu A nu is bigger than zero. Well, it could be equal to zero, but only in the case that A mu is really the zero vector. This could be true, yeah? U mu can never be the zero vector, because it must be a tangent vector to a line, not just to a point. But the A mu can be zero. What would this be for a curve for which the A mu is identically zero? A mu is this. If this is identically zero, what does this mean? Yes, it would be a straight line, right? The tangent vector would be constant, and a curve is a constant tangent vector. That's a straight line. So for a straight line, this would be identically zero for all four components. Then, of course, the thing would be equal to zero. But in any other case where I do not have a straight line, I really get a strict inequality here. Okay. So we know already now two special kinds of motion. Special cases. So the first one is uniform motion. Uniform motion, this means A mu equals zero. Word line is a straight line. So that's a rather trivial case, but of course an interesting case, because this defines the inertial motions, right? The motions where no forces are acting. Then in the second worksheet, you treated a uniform rectilinear motion, I should write. Sorry, uniform rectilinear motion. Yeah, motion in a straight line. The linear motion. A mu equals zero. And now uniform circular motion. Yeah, I'm in an inertial system, and now my particle moves in a circle with constant speed. That's what we call uniform circular motion, and that's what you discussed yesterday. See second worksheet. And now we will do a third example, which is slightly less trivial. This will be motion with constant acceleration. In a straight line. Yeah, so I have a motion where the particle accelerates with a constant acceleration. It always moves in one line, so it's a rectilinear motion, but not uniform with constant velocity, but with constant acceleration. Yeah, so the velocity, so it will be a quadratic motion with respect to the spatial coordinate. And of course, I can always choose my direction as the x1 axis with constant acceleration in the x1 direction. Let me spare this space. In the x1 direction, and that's what we will now do together. I do this in fairly great detail, and there's a reason why I do this, because the observers which we get here, they're the so-called Rindler observers, they will accompany us for a while. they will play a crucial role when we talk about the equivalence principle. Because the equivalence principle, as most of you already know, roughly speaking says that uniform acceleration is the same as being in a gravitational field with a constant gravitational field strength. So when we mimic gravitational fields, that's what we will do next week, then this sort of motion will help us in order to replace the gravitational field by an acceleration. And this will allow us, just in a kinematical way, without talking about field equations or things like that, to study things like the gravitational redshift, for instance, or the gravitational light deflection in a constant gravitational field. So these observers will later play a great role, and that's the reason why I discuss them in some detail. So how would this look like? So how would the x mu look like? So obviously, so I write this in the way x mu of tau, and I put brackets around this. By this I mean the column vector. Yeah, the column vector with components x0, x1, x2, x3. That's what I mean by x mu in brackets. So because the motion is in the x1 direction, two components are 0. I have only here two components, so I have an x0 of tau and an x1 of tau, and then two zeros. And just to simplify notation a little bit, I can write this as c times some function t of tau, and for this I just write x, because I have no other coordinates around now, so by using indices. So that's the way in which I write it. And the goal is to determine t and x, these two functions which are undetermined until now, to determine these functions in the way that I get motion with uniform acceleration. So obviously the velocity is then, I squeeze this here. The velocity, that was the derivative with respect to tau, right? So I just take derivatives. So this is c dt by d tau. From some point on, I will drop the arguments tau. Yeah, it becomes a little bit tedious to always write them. But actually, we should always keep in mind what depends on tau and what does not depend on tau. So that's the u mu. And the acceleration, I can also write here. That's, again, the differentiation with respect to tau. So now I get the second derivative here. The tau squared, second derivative of x, the tau squared, and then two zeros. OK, I have two functions, t and x, which I want to determine. Obviously, I need two conditions. So which two conditions would determine these functions? Any suggestions? What sort of properties have these expressions to satisfy? Well, I claim that there's one condition which every word line has to satisfy, which we have to use, and then the other one which specifies that the acceleration is constant. So what's the general, the universal one? Which would you suggest to use which equation? Tau is proper time. So I think you did this yesterday also for the when you did the last problem on the world sheet. You needed this condition in order to find out how t in your problem was related to tau. There will be a different relation, of course, which we get here. So what you use is this normalization condition. That's the definition of proper time. And it always tells you which normalization condition the tangent vector has to satisfy. So we have two conditions. So the first one, let me write p1. So this is minus c squared is eta mu nu u mu u nu. And the second condition? So now we want to write that the acceleration is a constant. So where is the acceleration? Here is the acceleration. And this is a spatial vector. So if I write this thing here, what's the sign of this? This here was negative, right? Because it's a vector inside the light cone. What's the sign of this here? I think it's still on the board. Yeah, there it is. This is positive. So if this is a constant acceleration, then this should be a positive constant. Let's call it a squared. Yeah? Where a is a constant. So these are the two conditions we have to satisfy. And now let's write this out. So let me try. I think so for our word line, let me write it again in a new line. So the first condition is minus c squared is eta mu nu, u mu, u nu. So this is this term squared with a minus sign plus this term squared with a plus sign and then two zeros. Yeah, so this time squared with a minus sign. And this is minus c squared dt d tau squared. And then with a plus sign, this here squared. Yeah, this is eta 1, 1, x1 squared. So this is dx by d tau. So that's the first condition. And the second condition is the analogous expression for this here. This squared with a minus sign, minus c squared, second derivative, squared plus second derivative of x squared. Now there are various ways, and what you see is a system. What you get is a system of differential equations, right? You have to solve a system of differential equations for the unknown functions x of tau and t of tau. Well, and there are various ways of doing this. The clever way is to carefully look at this equation and then make an ansatz. You see, you remember hopefully the identities for the hyperbolic trigonometric functions. So you see, if you have something of the form a squared minus b squared is 1, and that's the form of this equation, right? A squared minus b squared is 1. Then it's always a good idea to substitute for a and b the cosh and the sinh of something. Then this is identically satisfied. Yeah, if you had plus signs everywhere, then you would do this substitution with sine and cosine. But if you have a minus sign, then you have to do it with cosh and sinh. So b1 can be satisfied, is automatically satisfied by the ansatz. So let me begin. So if I multiply everything with minus 1 over c squared, then I get a plus 1 here. So this should be the sinh, 1 over c dx by d tau should be sinh of something, which I denote by f of tau. That's a substitution which is always possible, right? Sinh is a function which is monotonic on the interval from minus infinity to plus infinity. So it doesn't restrict this expression in any way, as long as I make no particular assumptions about this here, right? As long as I say this is any f, which at the moment I don't know, this is just a universal substitution, which I can always do. And if I have done this, then of course it's clear what the other term does. The other one, dt by d tau, must then be the cosh of the same thing, f of tau. And with this ansatz, I have the first half of my equations already satisfied. I think I should use this space here. Oops. So now everything boils down to a condition for this function f alone, and the condition is given by this equation. What is this funny sign here? There's nothing. This is just plus a squared on the left-hand side. So B2 now requires what? B2. Okay, let me do it quite slowly. I have a squared on the left-hand side, and here I have minus c squared, this squared. No, sorry, the derivative. Yeah. Here I have substituted for the first derivatives. So here I have second derivatives, so I get something with f prime, right? So I have this minus c squared, and then the derivative of the second derivative of t squared. Here's the first derivative, so I have differentiate this with respect to tau and then square it. So I get derivative of cosh is sinh. The nice thing with the hyperbolic functions is that you always get a plus sign if you have derivatives. Yeah? With sine and cosine, you always have to keep in mind where's the minus sign. With the trigonometric functions, you always get plus signs. F of tau and the inner derivative is an f prime of tau, and the whole thing squared. Yeah? So this is second derivative of t with respect to tau, and this squared. And this expression here is, okay, I have to take this to the other side, then I get plus c squared, and now the derivative of sinh. So this gives cosh of f in tau, f prime of tau, the whole thing squared. And this very nicely gives cosh squared minus sinh squared, which is just 1. So this gives plus c squared f prime of tau squared. That's it. Yeah. And of course I can solve this for f prime, and I get plus or minus a over c. So that is still a differential equation, but now a very simple one. Everyone can integrate this, right? This is easy to integrate. So the general solution, of course, is f prime of tau is plus minus a over c times tau plus an integration constant. No prime here, f of tau, which is f of some tau naught. Actually, tau naught is 0. Yeah. So that's the solution. Well, so there are two ambiguities. There's a plus minus sign here. Well, that's easily understood because I can have the acceleration in the positive x direction or in the negative x direction. That's why I get a plus minus sign. I can absorb this into the a. Let's agree to take a positive, it's in the positive a direction, and a negative, it's in the negative a direction. Yeah? So absorb the plus minus sign into a. So a can be positive or negative, depending on whether the acceleration is this way or that way. And well, what's the physical meaning of this here? Well, where I put tau equal to 0, that's up to my choice, right? I have a standard clock, it has a dial, and where do I put the 0 on the dial? Yeah, that's the question. I can put it anywhere I like, so I can set this equal to 0 without restricting the generality. Absorb and choose 0 on the dial of the standard clock. Remember, a clock which shows proper time is called a standard clock. Yeah? So when we parameterize a world line with proper time, this means we give a standard clock to the particle. 0 on the dial of the standard clock such that f of naught is naught. So then we get simply f of tau is a over c times tau. So that's our world line. We can now. So this gives us the first derivatives of x and tau. So we have to integrate this another time in order to get x and tau itself, x and t itself. And then we can discuss what this is geometrically. So I think I should leave this for latecomers. So maybe I can use this space here a little bit. So this this was our function f of tau, right, which we have now determined. So I have now dx by d tau is c times sinh of a tau over c, and dt by d tau is cosh of a tau over c. And of course, this can be easily integrated. So we integrate this another time. And then we get x of tau is c times cosh a tau over c. If I take the derivative of this, I get the sinh, and I get a factor a over c. And because that's not there, I have to write it in front here. Yeah, then it gives this here. So if you differentiate this, you reproduce this. And analogously for t of tau, we have something proportional to sinh. And I differentiate, I get a factor a over c, and I have to kill this, so I need c over a. Okay. Does anybody see what sort of curve this is? Well, let's say if this would not be a cosh and a sinh, it would be an ordinary cosine and a sine. What sort of curve would it be? Oh, I forgot the integration constant, sorry. Of course, I have an integration constant here and an integration constant here. But that's irrelevant, yeah? So if this would be an ordinary cosine and an ordinary sine, what sort of a curve would this be, which is given in the xt diagram? That's the x-axis, that's the t-axis. Well, you knew this. You did it yesterday. Well, with the cosine and the sine?
Would be circle.
Then it would be a circle. Well, almost. If the factors would be the same. Yeah, if the factors would be the same, then it would be a circle.
The factors are the same if we take the c in the first.
Oh, if you, yes, okay, right. Okay, you're right. Perfectly right, yeah. If I do it this way, yeah. and that's what we usually do, we plot x and ct. So then it's a circle. You're perfectly right, yeah? So if you have different factors here, it would be an ellipse, yeah? But you're right. If you do it in this way, and that's the proper way of doing it, then you get a circle. And now it's not cosine and sine, it's rather the hyperbolic cosine and the hyperbolic sine. And, well, some of you already suggested that then we don't get a circle, but rather a hyperbola, right? And if you want to see this, you can easily see this. So this implies, I think the easiest way of doing this is to writing it in this way. X naught squared minus c t of tau minus t naught squared. Now I have to get the factors. No, it's okay. It's okay. I have c, of course, also here. C t naught. So then I have this expression squared minus this expression squared, and this is just c to the 4 over a squared, right? Multiplied with cosh squared minus sinh squared, which is 1. Yeah? And now I think now you see that this is a hyperbola, right? With a plus sign, it would be a circle of this radius here. The radius squared would be this expression. And with a minus sign, it's a hyperbola. So if you plot it, you get something of this sort. Where should I write this? Maybe here. So I got integration constants, x naught, ct naught. And that's the values by which I have to move my origin in order to bring the hyperbola to standard form. So this would be the natural origin for the hyperbola. So I get something with these asymptotes here. So that's what I get, a hyperbola of this sort, right? So that would be our x mu of tau. And that's indeed something with a constant acceleration. The constant acceleration is in the positive x direction for this diagram. For the negative x direction, I would get something like this here with a negative a, yeah? For the positive a. So the particle comes asymptotically with the speed of light. So it comes very, very fast from the positive x direction. And then the acceleration slows it down. Yeah, so it becomes slower, slower, slower. This means the world line becomes more and more vertical. Here at this moment, it is at rest for one moment. Yeah, so it slows down, comes to rest at one point, and then it re-accelerates into the positive x direction, becomes faster, and approaches the light cone again. So that's precisely the world line we have already studied in the first worksheet. Yeah? You remember this? This was one of the two mirrors which we used when we had the light signal bouncing back and forth between two mirrors. And that's precisely this motion with constant acceleration, which, as I said already, will play an important part later. So that's how it looks in a space-time diagram. So what does the value, the absolute value of this A tell us? So if I make A bigger or smaller, what would change with the picture? You have an idea? So if I make the A very, very big, if I have a very, very strong acceleration, well, what changes is how close this is to the light cone. Yeah, it becomes closer to the light cone. It becomes it's very narrow to the light cone. So the common feature is that it's always asymptotic to the light cone, but how fast it approaches the light cone, this depends on the A. Yeah, the bigger the A, the closer it will come to the light cone here. Okay. This isn't, I mentioned this already when we did this problem in the first worksheet. This is an idealized sort of motion, of course. Nobody can realize this for the simple reason that you would need an infinite amount of fuel for keeping on this world line, right? You have to accelerate. And at some point, you run out of fuel and you cannot accelerate any further. And then in reality, you would actually do a motion like this. You would come to a slower motion. But as a mathematical idealization, we can think of a rocket or something like that with an infinite amount of fuel, and then you could stay on this world line forever. So that was the third and actually the most interesting and most important example I wanted to do for world lines. And now, so this was for velocity and for acceleration, two important notions. And there's another important notion which we will need. So this brings this example to an end. The another motion is the form momentum. And for that we need the mass. So we assign a mass to each particle. We assign a mass. And when I say mass, I always mean the rest mass. I never use anything else. Yeah? So for this reason, there's no, I never put a subscript to the M. M always means rest mass. I never use anything else. So that's a quantity which characterizes the particle, and it does not depend on the inertial system I've chosen. It really characterizes the particle in a universal way. And of course, you can ask yourself, how can we measure this rest mass? And we will do a little exercise about this in the next worksheet, where we will see that it can be actually measured by collision experiments. So we will talk a little bit about collisions of particles. And we will then see that if we have a particle with a known mass, for instance, a particle which you call our standard mass, and you let it collide with another particle, then we can deduce from the observed world lines the mass of the unknown particle. So it's really a measurable quantity. So the third worksheet. So I leave this question open for a moment. For a moment, we just assign this parameter to the particle, and we talk about the measurability later. Then we define the form momentum. So I denote p mu, supposed to be a small p mu. And this is just m times u mu. Now the u mu, so you may view this as a definition of the form momentum of a massive particle for the time being. So as a u mu is normalized, this was our proper time condition, also this p mu satisfies the normalization condition. So only 3 of the 4 components are independent. Yeah, the normalization fixes the 4th one. Let's work this out. So from this equation we find the following. If I calculate this expression, then this obviously gives me m squared eta mu nu u mu u nu, and this is minus c squared. So the whole thing is minus m squared c squared. So this means I can express one of the coordinates of the form momentum, and the natural choice is a time component. I can express one of them in terms of the other 3. So I can write this here, of course, as minus p naught squared plus p1 squared plus p2 squared. No, they have upper indices. Sorry. So, and for this I write just p naught squared plus the vector p, that's the usual 3 vector p, vector with components p1, p2, p3 squared. Okay, now you see that I can solve this for p naught, and I get p naught is plus or minus depending on whether we go into the positive or the negative time direction, and usually we choose the positive time direction, so it should be a future-oriented vector. And then I have the plus sign p squared plus m squared c squared. Okay? So that's the way in which we express the time component in terms of the spatial component. So the spatial components fix everything. Yes. Next thing is we want to express this by the 3 velocity. Remember, the 4 velocity u mu was related to the 3 velocity in a slightly confusing way. The spatial components of the u were not just the 3 velocity. There was this funny square root in the game, right? That's the reason why we distinguish them by letters. We use u for the 4 velocity and v for the 3 velocity. And the 1, 2, 3 components of them are different. So as we had this expression, u mu was ui was vi divided by the square root. Yeah? We get an equation where we can express the momentum, the form momentum, the spatial components, of course, only because this only involves spatial components. We can express the pi also in terms of the v's. And this gives me what? This gives me m times ui, and it's mvi divided by the square root. So you see the spatial components are not just m times the 3 velocity. That's the standard elementary textbook definition of the momentum. The relativistic momentum is more complicated. It involves the square root. So that's the equation for the pi. And if we like, we can approximate this by a Taylor expansion. So we can write the square root in this way. So this begins with a 1. And then I have minus 1/2 of the exponents. The square root is in the denominator. So I get a change of sign plus 1/2 v squared over c squared plus and so on. So you see the non-relativistic formula pi is mvi only holds if these terms can be neglected. If from the quadratic order on, all terms can be neglected. So if the velocity is small in comparison to c, then this is true, and then it can work with a non-relativistic formula. But if the velocity comes closer to the speed of light, then we can no longer do this. And for the p naught, we have the following equation. P naught is m u naught, and u naught was c over the square root, 1 minus v squared over c squared. Yeah, u naught, the 0 component of the 4 velocity was c divided by the square root. And again, I can write this as a Taylor series, 1 plus 1/2 v squared over c squared plus and so on. And this gives me an interesting equation. Namely, if I multiply this with c, then I get Cp naught is what? I multiply with c, so I get mc squared. And then I get mc squared divided by c squared. So this gives just an m. And then 1/2 v squared. And then I get higher order term. And this tells you how you can interpret this component P naught, or rather C times the component P naught, because this is something which everybody recognizes, right? That's just a non-relativistic kinetic energy. So this is a modification, a relativistic modification of the energy. Yeah, so that's a non-relativistic kinetic energy here. Non-relativistic kinetic energy. And you see in which way changes this now. First of all, there come higher order terms. Yeah, which are at least cubic in, or actually even quartic with respect to V over C. And then you get this term here, which is present even if V is 0. So according to relativity, the particle has an energy even if it is at rest. And that's the reason why we call this a rest energy. And the whole thing is then called the relativistic energy. And because we are talking about relativity here, so there's no need to use this adjective. So when I speak of the energy of a particle, then I always mean the relativistic energy, and this is just this expression. Yeah, so it's a time component of the form momentum multiplied with c, which most people said equal to 1 anyway. But so that's the interpretation. So the form momentum has 4 components. The spatial components are up to correction terms, the standard 3 components of the momentum, and the 4th component is the energy, which involves a new thing, which in pre-relativistic physics didn't exist, namely a rest energy, and then the non-relativistic kinetic energy and correction terms. And of course, everybody knows that this is not just a mathematical artifact, but this energy really exists and that it can be converted into other forms of energy, right? So that's what happens in the atomic bomb and in nuclear fission reactors. Yeah, the energy which is in this term here can be converted in other forms of energy, into heat, for instance. And this clearly shows that it is something which really exists in nature, which is not just a funny mathematical construction. Okay, so much for the form momentum. We will use this, of course, later. And in particular, we will use it in connection with the equation of motion for particles. So this is the equation which is the analog of Newton's second law. And in special relativity, of course, it has a 4-vector formulation. And it's just the same equation as a non-relativistic one, but now with 4 indices. So its force is a derivative of the momentum with respect to the natural parameter along the world line, which in relativity is proper time. And we will solve equations of motion soon for a particle in an electromagnetic field. That's what we will do, what we will begin tomorrow and probably finish next week. Okay, yeah. Okay, some people don't like it being called a definition, but from as far as the mathematical formalism is concerned, I think it is a definition. So I wanted to write that F mu, the force velocity, is defined as a derivative of the force momentum. So let me write it in this way: the force velocity, the force is given by. Now everybody can read this as he or she likes, either as a definition or as a law of nature. Of course, it's a function of tau, and it's just the derivative with respect to tau of the momentum. And this gives the equations of motion. And what does this mean? It means it determines the world line, which is hidden here inside the P, right? P is m times u, and u is a derivative of the world line x mu. So the x mu is hidden inside the P. It determines the world line x mu if f mu is given, and it determines this for any choice of initial conditions. And the initial conditions are, of course, initial position and initial velocity. So the initial conditions are x of tau naught, x mu of tau naught, and u mu of tau naught. So that if you tell me where the particle is, where in space-time at proper time tau naught, and what's the tangent vector, the forward velocity at this point, then this gives me a differential equation which has a unique solution for any given f mu. Of course, it is also a function of tau. Okay, and we will calculate equations of this sort later. Yeah, a warning, one should always write the equation in this form. The equation f mu of tau d tau p mu of tau is valid even if m, the mass, the rest mass, is a function of tau. Can you think of an example where a mass is a function of tau, where it is not constant? A reasonable physical object for which the m would not be a constant.
Rocket?
Yes, yeah. But yeah, it has gas, which it loses mass in the form of exhaust gases, and for this reason the m would be a function of tau. And you can perfectly well calculate this with this equation. So in this case, let me write this explicitly. I have this here as d by d tau. Now of f of tau, m of tau times u mu of tau. And this is, of course, if this depends on m, if the m depends on tau, this is not the same as m of tau times the acceleration. Yeah? So if you always work with this equation, and don't talk about maybe this depending on tau or not, then you are not covering the most general case. Yeah? So the force is not mass times acceleration in general. It's a time derivative of the momentum. That's the general formulation. By the way, it's historically quite interesting that Newton, in his three-dimensional formalism, of course, never wrote the equation F is m times a. That's the way in which we nowadays learn Newton's second law usually. He always write F is, well, in modern letters, d by dt of p. He used a capital G for the momentum, and he called it Bewegungsgröße in German. What's that in English? Quantity of motion or something like that. But that's precisely what in modern physics is called as a momentum. So he never used this form, m times acceleration. He always used this form, time derivative of the momentum, and that's a universal thing. So that's more general than the form which is more familiar to most of us. Okay, so much for particles at the time being, but we come back to this. So tomorrow we will talk about the electromagnetic field, and then we will discuss charged particles in electromagnetic fields. And this will be a nice application of this equation. So this will be solved for the case that the force is the Lorentz force. Yeah? The force which comes from an electromagnetic field. That would be a standard example for this. But this section about massive particles ends here. And I will now tell a few things about particles with rest mass equal to 0. That's what you might call a classical photon. Or just a photon, but for the sake of clarity, let me call it a classical photon, just to emphasize that, of course, I do not talk about some quantum properties. So a classical photon is just a particle which moves at the speed of light in a straight line, period. So, so it's a classical model of a photon. And that's also allowed. That's also a signal, right? I can also use these as signals. What is not allowed is particles or something which moves at a speed bigger than the speed of light. So the usual terminology is, if we say just particle, we mean something which moves at a speed slower than the speed of light. And if we want to consider this case that it moves at the speed of light, yeah, then we call it a photon. Okay, classical photons can be defined. Defined as objects moving uniformly on straight lines with speed c. And this is a major difference to particles which move at a speed smaller than the speed of light. For particles moving at a speed smaller than the speed of light, we had introduced this important parameter tau, the proper time, and we had expressed everything with the help of this tau. Yeah, the forward velocity was defined, no, it's no longer on the board, the u mu, the forward velocity was defined in terms of proper time. So if it wouldn't be possible to introduce proper time, the forward velocity would not be defined uniquely, right? And that's exactly the problem which we encounter when we talk about particles moving at the speed of light. We will see that then proper time is no longer defined. And this is easy to see, namely, remember this relation, in which way did I write it, dt by d tau or d tau by dt? Let me write it dt by d tau, then I have the root in the denominator. Let me write it in this way. Yeah, that was the relation between coordinate time and proper time. And we see if I now send the v to c, if I approach the situation that the particle moves at the speed of light, then I get a 0 here in the denominator. And this means yeah, the derivative must become infinite, right? So the tau is no longer, the d tau is no longer defined. Because for v to c, we have, yeah, let me write it in this way. D tau goes to 0, yeah, in quotation marks. And this means that, yeah, some people express it in the way that they say proper time stands still for light, yeah, for something which moves at the speed of light. Yeah, so the tau is no longer increasing. It stands still. Well, it's, you shouldn't take this formulation too serious, but at least in quotation marks, I think one can write it down. Actually, that was the question with which everything started for Einstein when he was 16 or so. He started thinking about what happens if I'm riding on a light ray. Yeah, what do I see around me in the world? And after thinking about this for 10 years or so, he came up with special relativity. And the answer was you cannot ride on a light ray. Yeah? If you're a massive body, if you have a mass, and then you have to move always at a speed smaller than the speed of light, so you cannot ride on a light ray. And if you could, you would see that proper time would stand still. That's what this equation here tells you. So this means proper time doesn't exist for light. So for photons, there's no proper time, and as a consequence, there's no forward velocity. Yeah? Photons do not have a forward velocity. For photons, proper time is not defined. And this means, as a consequence, for velocity and for acceleration are not defined. acceleration are not defined. So, okay, should we close this section and say that's not a meaningful concept? No, because there was another quantity which we had introduced. That was the form momentum. And funnily enough, the form momentum can be defined for a photon. And for this reason, you can consider collisions and all sort of other things where the momentum plays a role for photons perfectly well. Yeah, you should never speak about the forward velocity or the forward acceleration of a photon, because this simply doesn't make sense. But you can safely speak about the form momentum, and we will do this now. So, however, the form momentum of a photon can be defined. And how do we do this? What we have to observe is that the form momentum was related to the let me write it in terms of the three velocity. So we had these formulas for particles: m vi divided by the root, and what was it? C p naught was mc squared divided by the square root, right? Well, actually, I can divide by c. I can write it in this way. And so we see if we want to have the p well defined. Oh, this has an upper index. Sorry. And v equal to c, then we see there is a way out of this. Namely, we have to assign the rest mass m equals 0 to the particle. Yeah? So this is supposed to be finite. We want to have a finite pi. This here becomes 0. So the only thing, and this is the only way in which this can work, is that this also becomes 0. So the way is the way out is that we say the mass is 0. And the same thing here. Yeah, here you see it even better. Yeah? If this is supposed to be finite, and because this becomes 0, this also must become 0. And because c is definitely not 0, the only way is to say m is equal to 0. So because this, p mu can be well defined for v to c if we assign the mass m equals 0 to photons. So we say a photon is a particle which has a form momentum, p mu, and of course this must be light-like, yeah, because the world line is under 45 degrees, so it should be should move with speed c. So the form momentum obviously must be light-like, and the mass must be 0. You see it also from this equation. Maybe that's even a better way of seeing it. We had this equation here, right? You see, if you want to have this light-like, and that's what you want to have for photons, so this should be 0, then again you see this only works if we set m equal to 0. Yeah, so everything fits together if we consider the situation in the suggested way. So in summary, a photon is a particle, particle in quotation marks, with light-like form momentum. And this means that eta mu nu, p nu is equal to 0. And 0 rest mass. I usually just say mass when I mean the rest mass. M equals 0. Okay, and now we can see what we can do with these things. That's a formal definition of a photon. Yeah, we had this relation between this expression for the energy. The energy was this here. Actually, I didn't denote it by E. So the usual letter which I use for this expression is E. So let me call this capital E. So capital E was C times P naught. So it was mc squared over the square root, which only works for particles. And we can now see what we get for the energy of photons. So we can write E is C times P naught. The energy is then, so the energy was this here. And now I have something with a light-like form momentum, P naught, that's an upper index, sorry. So this is in this case, okay, let me write it quite generally in the beginning. So this is the square root of P nu minus P1 squared minus P2 squared minus P3 squared. Hope you can read this. No, what did I do? That's nonsense. No, I cannot write it in this way. I mixed two formulas into one. And so what I want to use here is that this is P naught squared with a minus sign, sorry. Minus P naught squared plus P1 squared plus P2 squared plus P3 squared, right? So for photons, we have that this expression is equal to 0, so I can solve for P naught, and then I got C times the square root P1 squared plus P2 squared plus P3 squared, or if you like to write it in this shorthand way, it's C times P absolute. Oops. So that's the relation which holds for photons, right? So the spatial components of the momentum determine the energy. And on the basis of this observation, we can now calculate a few things. I will calculate two effects which you certainly know very well, which you may have seen the final formula several times, but maybe you haven't seen a derivation with the help of this photon picture. Namely, the effects are the Doppler effect and the aberration formula. So I guess you have seen this with the help of wave ideas being derived. And I want to demonstrate, just as an application of this particle picture, I want to demonstrate that you can derive the same formulas in the particle picture with the help of these equations. So we will now derive the Doppler effect, which tells us, well, in the particle picture, how the energy of a photon transforms from one inertial system to another inertial system. And we will calculate the aberration formula, which tells us how the direction from which a photon comes changes if I go from one inertial system to another one. So I think that's a fairly instructive application of playing around with 4 vectors, and that's why I do it here. And the result, of course, is something which should not come as a surprise to anybody. So I think the final formulas are well known to everybody. We will use this photon picture, this picture of light being made up of particles that moves at the speed of light. We will use this picture also later when we do general relativity. Then they will not move on straight lines, as I do in special relativity, but rather on something which we call light-like geodesics. So this picture of a classical photon will accompany us through the whole term. Okay, So as an application, let's derive the Doppler formula and the aberration formula. In terms of classical photons. So these effects obviously involve two inertial systems, right? We ask how does the energy transform from one inertial system to another, and how does the spatial direction of a photon changes from one inertial system to another. So we have to consider a photon in two different inertial systems. So let's begin with one. Consider classical photon. With form momentum P mu. And we choose one observer. Later we will do a second one, and then we transform from one to the other. Choose an observer with constant for velocity u mu. Okay, so here's a picture. So you may think of this observer as being at rest in your chosen inertial system, but that's not necessary. You could also represent it with the help of another inertial system. That's ignored. So here I have my classical photon, which moves on a world line under 45 degrees, and it has a form momentum which lies also on the light cone. But the length of this thing has nothing to do with the proper time parameterization. The length of this thing is a measure for we have it. It's actually no measure of anything physical. So it's just mathematically assigned to this particle. And now I choose my for velocity in this way. And I can do the following thing. I can decompose this vector into a component parallel to u mu and into a component perpendicular to this. And the way how this component transforms gives me the Doppler formula, and the way how this component transforms gives me the aberration formula. So let me do it in this way. Decompose. Decompose P mu in components, or in two components, I think one should say, parallel and orthogonal. And when I say orthogonal, I always mean orthogonal with respect to the Minkowski metric to u mu. So I write it in this way. I introduce a vector n mu, which is perpendicular to u mu. And for some reason, I do it in a way that I let it point in the opposite direction as a p mu. That's the usual convention. If you derive the aberration formula, you want to consider the direction from which the photon comes. Yeah, so you choose a direction vector which points towards the photon. Yeah, so the photon comes from here, and this vector points into the direction from which it comes. That's the usual convention. That's the reason why I get a funny minus sign here. So I write this, no, sorry, the other way around. I begin with p. So I write this as a linear combination of u mu and this vector n mu. It's not an eta, it's an n, little n. Hardly readable, sorry. That's a little n. So. And for the reason I just explained, I put a minus sign here. Yeah? Then I get a factor beta here and a factor alpha here. With this thing here, eta mu, that again looks like an eta, n mu, eta mu nu is equal to 1. Yeah, it's just a unit vector. And it's orthogonal to n mu u nu. And the convention is we choose alpha and beta positive. Alpha positive means our photon has a momentum which is future oriented. That's the usual choice which we make. And beta positive means the direction is a direction towards the photon, as I explained already. So the signs are conventions, of course. You just have to see that you stick with it for the whole calculation. And now we can determine the coefficients alpha and beta. So obviously they must have something to do with the u mu and the momentum. What do I calculate first? Let's first consider the fact that the p mu is light-like. So I have eta mu nu p mu equals 0, right? Because we are considering a photon. Photon has a light-like form momentum. And okay, with this expression I can now multiply this out. I get alpha squared eta mu nu u nu. Then I get 2 times the mixed term, minus 2 alpha beta eta mu nu u mu n nu. And then I get this here with a beta squared eta mu nu n nu. So I realize that my etas look very similar as my n's, but you can distinguish them easily because if it comes with 2 indices, then it's an eta. And if it comes with 1 index, then it's an n. Okay, so what is this here? Question to the audience, what is this? Do we know this? That's
C squared.
yeah, very good. That's minus c squared. What is this here? Well, it's written here. Yeah, the two things are orthogonal, so this is 0, and this is a unit vector, so this is 1. And so we get one relation which connects alpha and beta. So we have that for which quantity do we want to solve? Both are positive, right? Both are positive. And then I have beta is alpha times c, yes. So beta is alpha times c. And I can insert this into my expression for p mu. So I can write an alpha in front of the whole thing. And then I get u mu minus this c here times eta mu. N mu. And this makes sense. Look at the dimensions. N is a unit vector, so it has no dimension. With a c here, it becomes a velocity, and that's also velocity. So I subtract 2 terms with the same physical dimension. So question is, what's the meaning of alpha? So the meaning of alpha becomes clear if we go to the rest system. In the rest system of the observer, whose velocity is u mu, we have, so u mu is then just c 0, 0, 0. The n mu is purely spatial. Yeah, it's perpendicular to the time axis, so this is n1, n2, n3. And then we can calculate which scalar product? So we have P naught in the rest system of, we have this here. Hence the energy of the photon is something which is related to alpha in the following way. So we have E is C times P naught, remember? E was C times P naught. And I hope we have something which connects this with alpha. Yes, of course, this equation here. C times P naught is alpha times U naught. Yeah, it's this equation here, alpha C times U naught. That's it. P naught is this here. Yep. N naught is 0. U naught is U naught, which is C which is again C. So I have this equal to, yeah, and that gives me alpha in terms of E. Hence the energy of the photon is, so I can write alpha as E divided by C squared. That was the formula I was looking for. So in summary, we have now our expression for the form momentum. We had this expression here, and alpha is now E over C squared. And then I have U mu minus C N mu. That's it. So you see you can express the form momentum in terms of the spatial direction vector, which tells you from which direction the photon comes, and the energy. And these are the two quantities which we want to transform, right? The transformation of E gives us a Doppler formula. The transformation of this gives us the aberration. So that's the formula we wanted to derive. So we have now the momentum in terms of the relevant things. And we write this down for two different inertial systems. And then we see what you can find for E and for N. So I have 10 minutes. Okay, let me see. I think I will only finish the Doppler formula. I need some more space. So I write this decomposition now 2 times for 2 different observers. So for 2 different observers, we get what? We get P mu is E over C squared U mu minus C N mu. And now for the other observer, I will have another energy, which I call E tilde. C is, of course, C. C doesn't change. It has a forward velocity U mu tilde, and it has a spatial direction N mu tilde. Okay? And now I have, from this equality here, I have to subtract some information about E and E tilde. That's the first step. I do this by considering an appropriate scalar product. Which one is the most intelligent way? Yeah, I write it in the rest system of the untwiddled observer. In the rest system of the untwiddled observer. Oops. So this means the U mu is just C 0, 0, 0. And the n mu is 0 and 1 and 2 and 3. And I think I also need the u tilde. Yes, u mu tilde. I should put brackets here because I mean the matrix which is formed of these things. So this has a this involves a relative velocity, which I call v. So I have a square root 1 minus vc over c squared here. And if you remember how the 4 velocity quite generally looks, here I have always a c, and then I have here the 3 components of the standard 3 velocity. Okay, and now I insert this into my equality. So I think I multiply with u mu tilde. Yeah. So I write this here, eta mu, and I multiply with u mu tilde. I hope this gives me the best expression. So what is this? So this gives, I'll write it first using the expression for the p on the left-hand side, right? Yes. So for this p, I insert this expression here. So I get e over c squared, and then I have eta mu nu u mu tilde. Then I have minus eta mu nu c. Let me write the c in front of the whole thing. And then eta mu u tilde. Okay. And I can read what this is. This here, eta naught naught gives minus 1. And then I have to multiply these two things together. So this gives c squared over root 1 minus v squared over c squared. And this here, I have to take the product with respect to eta of these two things. So I get a 0 in the first component. And then I get here n1 v1, n2 v2, and 3 v2, v3. For this, I write this here. Yeah? That's n1 v1, n2 v2, and 3 v3. And this square root. Oops. And I write it on the other side, now with the other expression here. So I use this expression here. Then I get e tilde divided by c squared, eta mu nu u mu tilde, minus c eta mu nu n mu tilde u nu tilde. Okay, that's minus c squared, and that's 0. And if I solve this for e, I get the desired equation. I think everyone can do this by him or herself. So if I solve this for e tilde over e, I get the following equation. Tilde over e is 1 plus nv. nv over c divided by the square root. And that's the Doppler formula. Okay, so this was the first thing. Then we will leave the classical photons for a while and talk about Maxwell's equation. Okay, so what I'm still planning in this section on special relativity will take 2 lectures, I think. It's Maxwell's equation and then a little bit on continuum mechanics on the energy momentum tensor and things like that. And then we can start discussing how we move to general relativity. So then the real stuff will begin. Okay, see you tomorrow. In this other room. Yeah, here it is, here in this room.